continue as well on your end. Okay, perfect. So this Desmos application really gives you a sense of what we're going to explore today in terms of instantaneous rate of change and the slope of tangent lines. So I'm going to stop sharing my screen and move back to sharing my notebook file. So we talked about the differences between average rate of change and instantaneous rate of change. And today we're really going to look at the difference between the slope of the secant as well as the slope of the tangent for instantaneous rate of change, and the definition of the slope of a secant line versus the derivative of the tangent line for instantaneous rate of change. Okay, so we're going to look at a particular example. It's a quadratic equation in vertex form. And instead of my x and my y, we're taking a range. We're starting at a particular x and taking an interval of what we're going to call h. So between this point x and the next point on the curve where we've drawn a secant line through those 2 points, we're labeling our x coordinate x plus h and our y f of x plus h. This is how we're going to describe the average rate of change between those 2 points, and it's going to help us develop our formula. Now, in the next slide, you can see like P and Q was our original secant line describing average rate of change. But if I draw another point R or another point closer to my point P, I am going to get closer and closer to the instantaneous rate of change. So in other words, the slope of the secant will get closer to the slope of the tangent line at P as we move closer and closer to P, and draw tangent lines that are as close as possible to P. And that's what we are going to be talking about today, because the real goal is to figure out the instantaneous rate of change. So this is a formula that you do need to memorize for your tests as well as your exam. So technically, the slope of the tangent line is the instantaneous rate of change. So the slope of the tangent line through a point on the graph of a function gives the function's instantaneous rate of change at that point. We use this difference quotient to help us develop our formula, where h is made to be a very small number. We're going to try to get the interval as small as possible in order to generate an increasingly accurate estimate of the slope of the tangent at a particular point x. Now, just like the graph I showed you, we can have the slope of the tangent at different points along the graph, but you will see that in a second. So we're going to take this function again. Remember, we're looking for the instantaneous rate of change when x is equal to 2. Now, using the difference quotient, I am going to pick an arbitrary value for h. So I could use h is equal to 0.00001. For the purposes of this example, I'm going to just pick 0.01, and I'm going to substitute it into the difference quotient. So the derivative of this particular function, I can use dy over dx, or I can use f prime of x, which I'm going to use in another example. Now, remember, this is an approximation. It's not exact. when I'm using the difference quotient. So I'm not going to provide it as an exact value. So that's going to be equal to, my formula said, f of x plus h. So my x is equal to 2, and my h value is going to be equal to 0.01. And we are going to subtract from that my f of x, which is f of 2. And we're going to divide everything by my h value, 0.01. Now, remember, this is the same when I say f of 2.01 minus f of 2. What I'm trying to do is plug this in to the original function to get these values. Now that's simple algebra. And when you plug it into your original function, you're going to get values. Now you want to keep as many decimal places as possible to make sure that these values are as accurate as possible. All divided by my h value, 0.01. So that's going to be equal to 1.198. Now, this is our approximation. So I want you to remember this value, 1.198. So this represents an approximate slope of the tangent at x is equal to 2. So by choosing an arbitrary value for h, we are figuring out an approximate slope of the tangent line. Now we're going to talk about how to use the exact find the exact slope of the tangent line, or exact instantaneous rate of change, using our Newton quotient. So before we saw, by picking an arbitrary value for h, that the smaller the difference in the x values, that would result into a smaller secant line. Let me just move this out of the way. And then that is how we get closer and closer to the actual instantaneous rate of change. But right now we're going to see, what if we put the difference in the x values at 0, so we can get as close as possible. This would give us the instantaneous rate of change exactly. However, in order to do this, we have to define the Newton quotient as the instantaneous rate of change by taking the limit of the difference quotient. And we call this the derivative from first principles. So dy over dx is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So we're going to take the concept of the limit that we learned about yesterday. Now I want to be very clear about this. Since the derivative is defined as the limit which finds the slope of the tangent line to a function, the derivative of a function at a particular x is actually the instantaneous rate of change of the function at x. Okay, so we define the derivative as the limit which finds the slope of the tangent line to a function. And that's what we're going to be using our alphabet, or the algebraic skills that you learned from grade 9 to grade 11 to solve and factor and simplify algebraic equations at this point. So we're going to do quite a long example. Today, I am really only focusing on quadratic functions for the first part of this lesson because it is the simplest type of equation. But after that, we will be looking at much more complicated functions starting tomorrow. So notice that this time I'm dealing with the exact same question, but I have expanded the question to make things easier. And we're looking to calculate the instantaneous rate of change when x is equal to 2. So the first thing I'm going to do is plug in my formula. Wherever I see x, I've replaced with a 2. So I'm going to figure out f of 2 plus h minus f of 2 over h. Now we're going to color code this, and we always leave the denominator alone. So I'm going to first figure out what f of 2 plus h is. Then I'm going to find out what f of 2 is, and I have to subtract and distribute the negative over there to solve that function. So to expand f of 2 means plugging in x is equal to 2 into negative 0.2x squared plus 2x plus 1. That gives us this component of the graph. And by plugging in 2 plus h into the same equation, I get this particular component, the yellow component of the graph. And I cannot forget the negative. If you forget the negative in between and do not distribute that negative, you won't be able to get the final answer. So as I solve in each of the brackets, I get a little bit further with the yellow component, the 2 plus h. That's going to take a few steps to completely eliminate the brackets and apply the distributive property. But once I've done that, I can get rid of the overall square brackets as I simplify further. Now notice that the positive 4.2 eliminates with the negative 4.2 once I distribute that subtraction sign. So the whole purpose of this is to keep going until you have a simplified equation. Now notice I'm always keeping my numerator and denominator separate, but there is a common h in both the numerator and the denominator. So I'm going to factor that h out. That helps me eliminate the h from my numerator with the h from my denominator. So I no longer have a fraction situation, a rational equation. And I finally have my equation in simplest form. Now, once you do that, wherever you see an h in the equation, we can replace that h with the 0, which will look something like this. So I'm not plugging in 2 into the equation. This is the equation of the tangent line at x is equal to 2, but I'm simply plugging in 0 into the equation. So I have figured out now the instantaneous rate of change at that particular point on the curve. So again, this is our instantaneous rate of change is 1.2. Now, you're not necessarily going to have a situation where your algebraic terms completely eliminate, and I'm going to give you an example of that next. So it is often useful when you're doing, you can see how many steps we just went through. So it's often useful to find the general equation for instantaneous rate of change that can be used to find the slope of the tangent at any point throughout the domain. This is called the derivative, and it can also be written as f prime of x. So we can write the derivative as dy over dx or f prime of x. I prefer, because most functions are written as f of x, I prefer f prime over x, but we can also write the derivative if the equation is y in the form of y is equal to, we can write it as dy over dx. Now, to find the instantaneous rate of change for this particular function, we're this time, because we're not looking at a specific point, we're probably going to find an equation that describes, a formula that describes the instantaneous rate of change. So when that happens, and we're not asked to find at a particular point, we are going to notice what I'm highlighting, take the limit as h approaches 0, so we can have an exact instantaneous formula for the instantaneous rate of change. Now, what I've done in blue is I've first, to make things easier, because the hardest thing and the component of the formula that students often get wrong if they're not being careful is f of x plus h. So before we start, I'm going to figure out f of x plus h and make sure that everything has been distributed and expanded, and that cuts down on the steps that we're going to have to do. So once we've simplified that part of the equation, you have to remember to distribute this negative. So notice, by distributing the negative and subtract, so it's minus f of x. By distributing that, every term in f of x has changed signs. Now, I've seen lots of tests where students don't do this properly, and this often results in a wrong answer. This will result in a wrong answer. So once we've simplified the numerator, you will notice that once again, there is a common h in every term of the numerator. So I want to factor that h out, so the h in the numerator can cancel with the h in the denominator. And so once I have a simplified equation, all that is left to do is substitute a 0 where I see h in the equation. So this time we don't have a value for the instantaneous rate of change. We have a formula. F prime of x is equal to 2x minus 5. We call this the derivative. Now we can use this derivative formula to solve for the instantaneous rate of change at exact points along the curve. So for example, if we've been asked to use the formula to find the instantaneous rate of change when x is equal to 3, well, I'm going to first write down my equation. The derivative is f prime of x is equal to 2x minus 5. And instead of my x, I'm simply substituting exactly what the equation called for. So we are going to group this, and I'm going to copy that. So instead of 2x minus 5, I have 2 times 3 minus 5. So the instantaneous rate of change when x is equal to 3 will be equal to 1. I can do, I believe there was another example. I guess I was wrong. When we move on to a very simple quadratic equation again, notice that once again, I'm going to solve f of x plus h first. So instead of negative 2x squared plus 7, I'm going to be substituting an x plus h squared. Very important that it's x plus h squared because the x was squared. If you just multiply by x plus h, you're not going to have that component of the formula correct. So you can see that all these skills that you learned in grade 10, grade 11, the binomial expansion, factoring, distributive property, all comes into play now. So if you don't know the alphabet of math with those particular skills, this will be quite difficult for you. But if formulas, manipulating formulas in algebra is a strong point, then you're going to do very well on this test. Now, again, we have to remember to distribute the negative sign. That will change the sign of everything in f of x, which is precisely what happens. We always want to factor out that common h to eliminate with the h in the denominator. So in this particular case, because I'm substituting h is equal to 0 when I have it negative 2h, my slope or my derivative of the function is simply going to be negative 4x. So the most important part of this is simplifying and solving everything correctly so you get the correct derivative so you can answer these questions correctly. Use the formula to find the instantaneous rate of change when x is equal to 3. Well, now that I have my derivative, f prime of x is equal to 4x, negative 4x. I should make that clear. Negative 4x. Now I can substitute x for different values along the curve to find the instantaneous rate of change at that particular point. Negative 12 when x is equal to 3, and positive 20 when x is equal to negative 5. And that is all for part 1. I'm going to stop sharing for a second, and we will, I'm just going to open another file. There we go. Okay, so opening Zoom back up, and I'm going to share the screen. Now, for many of you who might be taking math as a major component of their university program, or actually for engineers and certain career or educational pathways, I know Mr. Bullock and I, because we were math majors, we had to take a component that was called, or a course that was called math history, and I believe engineers also have to take that. So this is a little bit of a blurb for you to read on your own about Archimedes and his contributions to the whole concept of limits and limits approaching infinity, which we're going to touch upon a little bit tomorrow. So we're going to try to include little interesting facts in our lessons as we move along. So we're going to move back to this concept of one-sided limits, or considering limits from the left and the right. Now, instead of looking at a graph, for example, 1, I'm going to highlight a few things. First of all, remember the y values. We talked about yesterday our common sense definition of the limit, where the limit is approaching an intended height. So those y values are very important. Now, this is not a traditional table of values. You'll notice I don't have x is equal to 2, 4, 6, 8. I have this range of starting at 2. I have x is equal to 3, x is equal to 4, and then I have all these random little decimal places in between. And that's because I want to see that as I approach x is equal to 3 from the left, what is happening with our y values? And similarly, if I approach x is equal to 3 from the right, what is happening to our y values here? And you can see from in both cases, when I'm approaching from the left, so I go 2.5, 2.9, 2.99, I'm trying to get as close as possible to 3 without even without touching 3. You can see that my y values are approaching 7. And as I move towards and approach 3 from the right, my y values are also approaching 7. So the limit of this function x squared minus 2 as we approach 3 from the left, now I'm trying to highlight the superscript here. When you see a negative, that means I'm approaching from the left. When you see a positive, that means I'm approaching from the right. Because both of those values are the same, I can make the conclusion that the limit of the function x squared minus 7 as x approaches 3 is equal to 7. So this brings us through the important information that the limit of the function only exists if the following 3 criteria are met. First of all, the limit of the function as we approach from the left exists. The limit of the function as we approach a bound from the right exists. And both of those values, both of those limits have to be equal. And you're going to be expected when we ask you whether the limit exists or to calculate the limit of a function to make it very clear whether the limit and prove why, state why it exists or why it does not exist. So your communication is very key for the upcoming test. Now, piecewise functions will be on this test. And here's an example of a piecewise function. The name of piecewise functions is kind of very self-explanatory, but I included a graph here to help you understand this concept. So you'll notice that for the first component that I'm highlighting in yellow, x is not equal to 1 for that component of the piecewise function. This is what happens when x is less than 1. That's why we have an open circle at 1, and following all values less than 1, the function looks like the graph x minus 1. And it has a little arrow because it's going to continue going and going and going. Now, when x is equal to 1, we don't have a linear or we don't have an equation of a function. We actually have a constant value, and that's why we have a closed circle when x is equal to 1. And finally, when x is greater than 1, not when x is greater than or equal to 1, that's why we have an open circle, but for all values when x is greater than 1, we have this function that has a square root in it. So you can see that when we follow the yellow line, as we are approaching 1 from the left, the intended value or height of y, and see if I can do this, yeah, with dots. Well, y has an intended height of 0. So the limit of the function as we approach 1 from the left is equal to 0. Now, as we approach the limit of the function from the right, we would follow this blue line, and we can see that we're approaching the y value of 2. Now, because both of those limits are not the same, and obviously this function is not a continuous function, this means that the limit of f of x at 1, when x is equal to 1, does not exist, because the limit as we approach from the left is not equal to the limit as we approach from the right. And this is the beauty of piecewise functions. it allows us to compare different components of the function at the same time. So whenever it's good, whenever you see piecewise functions, even when they're not assigned to you, please practice this because they will definitely be on the test. Okay, so now we're going to explore two topics. First of all, I have a rational function, x plus 1 over x minus 4, which if you need review on rational functions, they are on my YouTube page, Miss Albert Math, MCR, and under MHF. Now, we know there is a vertical asymptote, but those of you who already know MHF also know that there's a horizontal asymptote because, and I have made a little note here for those of you who haven't taken MHF, if the numerator and denominator are the same degree, the quotient of the leading terms indicate where the horizontal asymptote will be. Now, the leading terms for both our numerator and denominator are 1, so I do expect a horizontal asymptote at y is equal to 1. So I'm just going to do a dot, dot, dot right over here. So we have a vertical asymptote and a horizontal asymptote. Now, our asymptote is at 4, and I need you to watch this very carefully as I highlight. As x approaches 4 from, oops, I don't want blue, I want yellow. As x approaches 4 from the left, you can see that we're not tending towards an actual y value, but we're going to continue moving on towards negative infinity. So as we are approaching from the left, our y values are approaching negative infinity. When I do the same as I'm approaching from the right, I am going to be approaching positive infinity. This is going to keep going up and up and up and up forever and ever and ever. So at x is equal to 4, this is not for the entire function, but at x is equal to 4, the limit does not exist because obviously negative infinity is not the same as positive infinity. However, we can do multiple limit questions for the exact same graph. So you'll see at the bottom, they're asking us to find the limit as x approaches positive infinity. Well, as x approaches positive infinity, and if you're not clear about positive and negative infinity, you really have to watch what I'm doing. So as x is moving towards positive infinity, that would be this direction. This graph is going to get closer and closer to the horizontal asymptote, which is y is equal to 1. However, as the graph approaches, x approaches negative infinity, the same thing is going to happen. It's going to get closer and closer to y is equal to 1. So in this case, the limit as x approaches positive infinity and negative infinity are the same. F of x is equal to 1, f of x is equal to 1. So we can analyze one particular graph using multiple different components of the graph, or x is approaching different numbers. And there will be a few graphs on the test. You're not going to have to draw the graphs, but you are going to have to understand how to analyze the graphs. Okay. Now, looking at an equation, that's why it's always a good idea to graph equations, because just by looking at this equation f of x, I know there's going to be a restriction. X cannot be equal to 1. And if I draw a table of values, I will figure out that at 1, x is undefined. However, with the table of values, you'll notice that as we approach x from the left, and as we approach at x is equal to 1, if we approach 1 from the right, or if we approach 1 from the left, I'm going to highlight that, our intended height of the function, that means our y values, are going to approach 2. And when I graph this, as I approach 1 from the left and I approach 1 from the right, the intended height of the function is going to approach y is equal to 2. So that means how I would write that mathematically, because as we approach from the left, f of x is going to, the limit of f of x at 1 is going to be 2 from the left and 2 from the right. That means the function does, or sorry, the limit does exist, and the limit is equal to 2. Even though there is a hole at that particular graph, the limit does exist. So this is extremely important for you to kind of take a snapshot of. When plugging x is equal to 1 in the equation, even though we get 0 over 0, because the function is not defined at that point, but it is not necessary for the function to be defined at a point for its limit to exist. This is the #1 mistake I see on tests. Students misunderstand this concept. You can have a limit exist even though a function is not defined at a particular point. By factoring, I believe you learned this in MCR, and we definitely learned this in MHF, you will discover that there is a removable discontinuity. So if we factor numerator and denominator, you will see by eliminating x minus 1, you know there has to be a removable discontinuity there, but we can solve the limit, and the limit is equal to 2. So by algebraically, or if you choose to solve graphically, you are going to discover that the limit does in fact exist. Okay, so I'm just included in our notes for more examples of direct substitution with some very simple functions. Now, with direct substitution, there will be some questions when there's direct substitution, but others where we need you to solve by first principles. So please keep that in mind. And actually, Mr. Bullock, I should ask you to stay for a bit, and we've got to discuss that for the upcoming test. But yeah, other than that, let's start my video again. And I'm going to stop our recording.